very much, everyone. Good afternoon to everyone. My name is Sam. I'm a member of Cohort 1 in the CCDC Molecules to Product, based in the University of Leeds. And as Jason just mentioned, my project is using polymorphophores to investigate structure-polymorphism relationships in small organic molecules. I think it'd be useful to start with some definitions for those who might need reminding or those who don't know. But crystal polymorphism refers to the ability of a single chemical entity to crystallize in multiple distinct crystalline forms, which each possess unique physicochemical properties. The performance of compounds when formulated into products is dependent on these physical chemical properties, which means crystal polymorphism is relevant to many different fields. One chemical field with a really obvious sort of connection to polymorphism is the pharmaceutical industry, and sort of the classic case, the academic case here for polymorphism's relevance in pharmaceuticals is the case of ritonavir. So ritonavir was a autoimmune deficiency syndrome medication which was released in the late 90s, and a insufficient polymorph screen was performed which identified form 1 ritonavir as the most stable form. So does anyone else probably with Benoit?
Yeah, Benoit saying he can't see them. Is that the case for everyone else or not?
I can see your slide on crystal polymorphism now. Benoit, you might want to log out and back in again. You might just need to leave and come back.
Yeah, it might be a good idea.
I've been having some issues myself today. Thanks for that. Form 1 ritonavir was discovered and formulated into the commercial product. However, these products began failing inexplicably around 6 months after release. And an analysis found that all of the ritonavir present in these formulations was a more stable and as yet undiscovered polymorph known as form 2. This meant that all of the product needed to be recalled and reformulated to the tune of billions of pounds, which ultimately served as kind of the watershed moment for polymorphism, and in particular polymorph screening as an industrial practice. So despite polymorphism being so relevant to many different fields, our understanding of polymorphism, and in particular in chemical features which influence polymorphism, is actually in its infancy. So one sort of key development or term that has really been exciting in the field of polymorphism for me is this idea of a polymorphophore. So a polymorphophore is a chemical fragment which, when incorporated into the backbone of a new chemical compound, has the likelihood has the effect of increasing the likelihood that this compound will display polymorphism. So anyone who's ever worked closely with medicinal chemists and things like that, this is a concept analogous to that of a pharmacophore in sort of those cases. It was a term coined by Maxger and his research group around 2008 when discussing a range of compounds, in particular compounds like ROY, compounds like the phenamates and N-phenylbenzamides. In recent years since this, other compounds have kind of been noted as potential polymorphophores, such as some barbiturate polymers. Studies into these polymorphophores, in particular into the N-phenylbenzamide and phenamate fragments, have found that structural analogues of these polymorphophores also display polymorphism, which is a kind of an interesting link there between sort of chemical structure and resulting polymorphic profiles. So we believe they're an interesting jumping off point for trying to find correlations between the chemical structure and the resulting polymorphism from that. Through our project, we have decided to investigate the ROY polymorphophore. This is for many different reasons, to be honest, but the first of which we decided that ROY, as it was used as a precursor to the synthesis of olanzapine, which is a anti-schizophrenia medication. We believe that ROI, whilst not being drug-like in itself, is somewhat drug adjacent and is quite an interesting compound to start as a baseline to start understanding sort of structure polymorphism relationships, SPRs. Another interesting fact about ROI is that it is in contention with flufenamic acid, which is a member of the phenamate group, which you may remember we mentioned previously, for the most solved single component crystal structures within the CSD. So basic terms, that means that ROI and flufenamic acid are in a bit of a tug of war for who is the most polymorphic compound present within the CSD today. So another interesting factor about certain polymorphophores is that they tend towards extreme polymorphism, which we believe by performing structural modifications around this polymorphophore scaffold, we can start to understand how small sort of chemical changes can influence changes in polymorphic profile. So that brings me on to kind of an overview of the project and what we're trying to do with the goals of the different stages of the project. The first thing we want to do is to generate a library of analogs of a polymorphophore. So for this project, we've decided to focus on the ROI polymorphophore, and we'll be focusing on small sort of 1 to 2 heavy atom structural changes to the scaffold. The rationale behind that we'll comment on in a second, but we're aiming to generate around 200 to 300 milligrams of each of these compounds for our initial sort of high throughput screen. Once that library has been synthesized, has been chemically characterized, and has had its solid forms characterized, we are then going to submit that library of analogs for a polymorphic screen. This will subject the compounds in that library to various different conditions, even some high throughput apparatus provided by my industrial sponsors over at Pfizer and Syngenta, in order to subject these compounds to different conditions such as different solvents, supersaturations, evaporation rates and temperatures, things like that, in order to ascertain the polymorphic profiles of the compounds within this library. And any sort of interesting compounds that we find from here. So in our case, I think a really interesting case would be if we get compounds that weren't displaying polymorphism. But any of these interesting compounds will be scaled up further synthetically in the lab, and we'll submit them for more rigorous polymorph screening. Once we have completed that polymorph screen and generated our large data set of solid form data, we are then going to analyze and basically mine through that solid form data in order to find commonly shared traits between the solid forms or the chemicals within this library. And we're going to be mining those common features against the CSD to see if they statistically relevantly form structure polymorphism relationships in a database like those such as CSD. And finally, if all goes well and we generate some very predictive SPRs, the most predictive of these SPRs will be combined to a machine learning model for polymorphic propensity. And ultimately, the gold standard of validation of these models would be testing against some unknown compounds. That brings me on to sort of the rationale and the design behind the library that we've constructed for these ROI analogs. Now, our study into the N-phenol benzamides has found that the polymorphophoric nature of these compounds is best sort of transcribed to derivatives when the changes to the chemical structure are small. So we wanted to focus on small sort of 1 to 2 heavy atom changes to the ROI scaffold. These small changes generate what we call a library of essentially matched molecular pairs. A matched molecular pair is any two compounds which are simply separated by just one heavy atom. So in this case here, benzene would be a matched molecular pair with chlorobenzene, but also toluene, only one heavy atom there. And matched molecular pairs are used again in various different settings. Another one is medchem, in which the differences in matched molecular pairs are used to rationalize what a small chemical change, what the influence of a small chemical change may have on, say, a toxicological profile or a solubility profile. And we believe that using the same rationale, that our library may help us ascertain what small structural changes, what influence they may have on the changes in polymorphic profile of our resulting compounds. Based on this rationale, we have gone out and designed, I think, 17 functional analogues of ROI based off this kind of matched molecular pairs rationale. We've gone for something that in the literature is known as a chloromethyl exchange, in which CH bonds within your compound are systematically replaced with C-methyl or C-chlorine bonds. And we also decided to do, just to expand the library slightly to probe some ideas or some old held ideas around polymorphism. We decided to do some functionalizations based on the functionality present within ROIs. So we're looking at this nitro group here and this nitrile group here. We're hoping that, this small chemical changes will help us understand the changes to the polymorphic profiles of the resulting compounds. So that brings me on to the library itself and how that's been going. I've kind of arbitrarily split the library just for ease of looking at it really into nitrobenzene analogues. So analogues focused around this left-hand kind of nitrobenzene ring here. And aminothiophenene analogues, which are based around modifications around this aminothiophenene moiety here. All of these compounds here were very, very simple to make, made by a simple SNAR reactions, quite nice yields, behaved quite nicely. And we are now in the process for these compounds here of starting to generate the solid form data and start to characterize some of the solid forms that we've got for this here. Within this part of the library, we also have lumped in this amino ROI here. So we've decided to reduce this nitro group here down to the free amine here. Now, a couple of reasons for this. One being that the nitro group has quite a strong electronic influence on the structure here, which we believe could be interesting just from a visual perspective of maybe the colors of the analogues. But another thing another notion that was previously held around polymorphism is one around hydrogen bonding, so hydrogen bond donors and acceptors, and molecular rigidity. So both of these were theorized to be like predictors of polymorphism, though both have since been kind of statistically disproven, or at least with the best data we've got. But we wanted to do this in here as the nitro reduced to an amine here reduces the number of hydrogen bond acceptors in the molecule. It also removes this quite rigid intramolecular hydrogen bond here, which is quite conformationally important for the molecule. And it changes the electronic profile of the compound. Brings us on to the, my thing's frozen, to the aminothiophenene analogues. These were made again via SNAR synthesis of the fluoronitrobenzene here with a base and the functionalized aminothiophenene here. The only difference here is the aminothiophenes weren't commercially available, so we had to make a lot of those in-house, which meant they were a massive pain in the arse to make for anyone that's interested. But yeah, we also in this group we also include the methylamine and royaldehyde, which are just simply a full and partial dibar reduction of this nitrile group here to get the methylamine and aldehyde respectively. Again, these have slight changes to the electronic profile of the compound, to the hydrogen bond donors and acceptors. Just thought these would be interesting modifications to add to the library. So now, that's what I've been doing over the past few months. What I'm up to now is finalizing and characterizing this library, including scaling up the compounds that I need to take forward for this high throughput screen. A lot of the sort of chemical analysis has been done, so I've assigned all the compounds chemically, so we know that the compounds that we've made are what we think they are, and we're just in the process of generating a lot of solid form data now for our library. This sums up the progress that we have with the library now. We're rushed for time. I'll kind of breeze through these last little bits, but the next stage of the project is to perform our high throughput screen of our compounds. However, since this is quite a new thing for my supervisory team and myself, we've decided to do some preliminary experiments on those compounds. We have a lot more material using the Crystal 16 apparatus, which has been provided for our use by the Roberts group over here in Leeds. This will allow us to get some information around solubility data, supersaturations, but also which solvents we are going to behave nicely with our compounds. Finally, in order to sort of inform our high throughput screen, we are going to be adapting a methodology which was used by Ferron and co-workers recently, known as polymorphic landscape calculation. This is a density functional theory or DFT-based calculation, which basically can provide you with a plot of relative energies of simulated crystal lattices for a given cell. So this was done by Ferron et al. To prove that most of, if not all, of the low-lying, low-energy polymorphs of Roy have been found. And we believe with small modifications to this code that we can find where the low-energy polymorphs of our Roy analogs are found and use this to inform our high-throughput screening. There are some references for anyone that's interested in reading some of the papers I've mentioned, and I'd like to acknowledge these lovely people here. Thank you very much for being patient.
A super talk. Thank you, Sam. So I'll open up to the audience here, and we'll have a few questions.
Time for Lawson.
Simon, fire away.
Nice talk, Sam. Thank you very much. Is there how do you discover one of these polymorph? How do you say it? Polymorphophores.
Polymorphores. It's a weird word, isn't it?
Yeah. Do they have any kind of consistent characteristics? I mean, is it electronic or proportional flexibility, or do you just have to discover them by looking?
I think so. Generally speaking, I haven't discovered any myself. The only ones that I know have been discovered by this Matska group, who is very interested in polymorphism itself. He seemed to be looking at them for sort of polymorphic reasons in and of themselves, but it does seem kind of empirical, kind of just experiment and see what compounds you get back. But if you were to just look at the examples of polymorphos, even if I do it here, even if I go back to sort of the slide over here with the potential polymorphophores, you can see there's some shared characteristics anyway. So like this kind of bridged ring system seems to show up a lot. Extended pi systems seem to show up a lot. I know one of the interesting compounds that I've seen that was surprisingly polymorphic was like tetracene, which is like 4 fused benzene rings. So which adjacent to this kind of disproves a lot of old theories around polymorphism itself, but there does seem to be shared characteristics within polymorphos, and I do think an interesting area of research around this would be investigating to find more polymorphophores, to look at characteristics shared within this group, and to see if you could go into polymorphophore design and start to think, well, yeah, we can start to define rigidly what is and isn't a polymorphophore from at least a chemical perspective, if not a properties perspective.
Yes, yeah. Do you know if there's any kind of connection between, or any correlation between tendency towards polymorphism and tendency to form high Z prime structures?
That's a good question. So the short answer is no, but one thing that I will mention is that the word correlation and polymorphism is like, it's a lot of things that we think would be correlated with polymorphism, but when you actually look at the data, when you do think, there's a great paper by Aurora Kruska-Baker, which I assume a lot of people have read, called Facts and Fictions around polymorphism, and it shatters really a lot of the assumptions, a lot of the anecdotal evidence that we have for polymorphism within the context of the CSD, which is the biggest data set we have. And if you're looking for correlations, you look there. So that's another cool avenue to search for, is to look for Z prime. I don't know if that was done within that study, but it's certainly something we'll look for within our library.
Yeah. Okay. Thank you very much, Sam.
Thank you.
Martin, do you want to go ahead with your unmute yourself and go ahead with your question?
Sure, yeah. Thanks for that, Sam.
Martin.
It's a very interesting way to go about looking for new solid forms, so I'm quite interested. I'm just wondering though, the fragments, the molecules that you've chosen to synthesize, do these run the risk of just simply complicating matters? So you're adding different hydrogen bonding acceptors and donors, but all of your fragments, they still share the same torsional flexibility around that central NH group. So I without knowing any of the data, my worry is that all of the molecules you've synthesized are going to be torsionally flexible and therefore have the ability to be highly polymorphic to some extent. And I don't know if it's going to help you to answer the question you've set out to answer, sort of thing.
Absolutely. Yeah, I think so. That's one quite it's a possibility that we have to kind of account for, is that every single thing that we screen here is just going to be really, really polymorphic, and it's not really going to tell us all that much about what we've done. We've in terms of like a relationship between structure and correlating that to polymorphism. We've done a couple to sort of poke at kind of traditionally held beliefs around sort of the origins of polymorphism, so hydrogen bond donors, removing that intramolecular hydrogen bonding thing. But another thing that I'm kind of hoping to find with this, we're kind of probing to just have a feel out around there, is that a lot of the correlations that the things that we used to think really correlated strongly with polymorphism don't seem to statistically hold. So if you look within, again, the best data set we've got really is the CSD. So if you were looking for maybe, you've got some proprietary in-house things at various different pharma companies or agrochemical companies, but the best data set we have available to the public is the CSD. And in the CSD, things like hydrogen bond donors, torsional flexibility, molecular rigidity just don't seem to correlate with statistically correlate with polymorphism within the CSD. So this is a little bit blind really. This is just looking at sticking stuff onto something that is quite polymorphically active and seeing what data that kind of spits out for us.
Yeah, I think whatever the outcome is, you're going to generate a real ton of useful information and data that can be mined and used in future. And just on that, just one more final one. I think it would be really interesting to look at the interactions of the molecules you've synthesized with ROI itself, and whether or not there were some that you could select as a subset and use as sort of an impurity to include in crystallizations to see if it has an influence on the outcome.
I like even co-crystals, or like, absolutely, using it as like a you use like polymer-induced nucleation and stuff like that. That could be like a template for certain geometries of Roy. One other thing which I really didn't mention here, which I've not mentioned machine learning much, but a big goal of this is kind of increasing the usability of databases like the CSD for data mining for machine learning. So if you're gonna data mine and do some machine learning based around polymorphism, then you need positive and negative data showing that something is polymorphic, something that isn't polymorphic. And by filling in the chemical space around a really polymorphic thing, we're hoping, it's a drop in the bucket, it's a million structures in the CSD, but we're hoping to sort of fill in that little bit of stuff, and to show if we could show that by making the CSD kind of more complete as a chemical space for certain things, we could start to get more correlations and start to understand how these compounds, or the polymorphism of these compounds in relation to each other. And it just make the quality of the data within the CSD more amenable to things like machine learning for this kind of task.
That's great. Thanks, Sam.
Thank you very much.
One other question, or two other questions I had for you, Sam. One was a really very simple one, which is, of the Roy compound analogues, do you see lots of different colours?
Not yet. Do you want to see some? I'm currently doing some XRD. So you've got
Okay.
What we've generally been getting is a lot of orange needles. These are a little bit wet.
That
But
probably
you
tells
get,
you something about which structures you should look in the CSD then.
absolutely,
From a confirmation
also,
point of view.
we've been using one solvent. So we've been using like DCM and various other things. So I'm assuming when we get to different solvents and stuff like that, we're going to get a lot of
seeing different colours.
different colours. But also the roymethylamine and royaldehyde, they're a much deeper red, a very, very deep red.
Yeah.
So yeah.
And on the observation about polymorphism and shattering, I think the levoflux, I still can't say it. The stuff Julia was looking at earlier, which is the two compounds, which essentially one is just the stereo, one is the racemate, one is a chiral center. It's fascinating that in that case you only see one polymorph with the racemic system, but you see massive variety. I think Jonathan Steed would probably start talking about molecular frustration, and one wonders if there's something in that. Anyway, right. Thank you for your talk, Sam. Thank you.